Hello, hello, good afternoon. Welcome to Worm Charming, Harvesting Malware, Lures for Fun and Profit with Pedram Armini from Inquest.net. Now, just a few brief notes before we begin. Please stop by the business hall located in Mandalay Bay, Oceanside and Shoreline Ballrooms, level 2 during the day, and the welcome reception is this evening at 5:30 p.m. The Black Hat Arsenal is in the business hall, level 2. You can join us for the Pawnee Awards. That's going to be today at Lagoon JKL, 6:30 p.m. Please put your phone in vibrate. Just silence your phones for everyone. And please give a warm welcome to our speaker today. Again, that's Pedram Armini. Thank you.
Thank you, Angelo, for the introduction. Good afternoon. Thank you guys for joining. My name is Pedram, and I'm here to talk about a subject that is something that I research pretty much daily. I find fascinating, and I wanted to share some notes that we've taken over time, as well as towards the end, announce a public data portal where you can essentially play with this kind of data and make similar discoveries on your own. You know, as a researcher, having access to data is critical. As time goes on, it's becoming more and more closed circles. So this is one of my attempts at giving back and exposing data for folks who are trying to get their feet wet in this world. So some quick background on who I am. Born and raised in New York City, living out of Austin, Texas now for the past 10, 15 years. Started off my computer hacking in the 1990s, with phone phreaking with red boxes and reverse engineering software with soft ice. I had gotten access to a laptop, didn't have any money to afford software, got soft ice and started cracking software just as a means of getting access to it. And in that process kind of learned, the tricks of the trade. I started off my career with a company called iDefense. We launched the Vulnerability Contributor Program, the first vuln buying program of its kind. Later, I kind of perfected that model by creating the Zero Day Initiative under Tipping Point. I've done a bunch of open source projects like PyMay, reverse engineering framework, Sully is a fuzzing framework. I've written a book on fuzzing. Actually, I can see my co-author sitting here in the audience today. Beyond that, I've done some startups where I worked on an antivirus removal product called JumpShot. That was sold to Avast, who were an advanced malware removal tool. And in recent history, I've been working on Inquest. We deal with these kinds of problems. In essence, we're a file analytics platform designed to solve problems for SOC analysts and SOC communities. So what we're talking about today, subject-wise, I chose worm charming. This is actually a real-world Texas sport. I mentioned I'm from Texas, and in East Texas, they have this competitive sport where through some kind of vibration, noise, or thumping on the ground, they're attempting to make these worms come to the surface. And so I thought that was pertinent to what we're talking about today, and I like that fun, side analogy. And so in our context, what worm charming is we're looking for interesting malware lures. We're going to harvest a giant corpus of malware from a variety of different sources. We'll be focusing on one particular one, and then we're going to be dissecting through those to try and find the interesting samples. There's a ton of malware samples created on a daily basis. Among those are some gems. Sometimes you'll even be able to find ODay that is being experimented with before malware campaign actually launches and goes like full production. So potentially as a defender, you might be able to get these like early warning signs and then produce either prevention or detection mechanisms to stop that kind of attack. I just don't want to stay here. So agenda-wise, what kind of lures we want to find, where do we go find them, how do we dissect them, and then which ones of these are interesting. And these pictures are not staged or fake or B-roll. This is a real competitive sport. That's a dude with a tuba trying to get worms to come to the surface of that field. So what kind of lures are we interested in? There's a lot of beautiful exploits out there. It's very hard to write exploits these days. The ramp up time is like a whole team for a year. You're chaining exploits together and you're jumping from one chip to another. But unfortunately, the reality of it is there's the two major types of breaches out there are either someone left their bucket open and all your credit card data has now been siphoned off by some person, or they're attacking the endpoint. They're attacking the end user. Either via some malicious attachment that's coming by email or drive-by download that maybe they're sending you a URL. These are your PDF documents, your Office documents, your Java, your Flash. Flash is dead in the browser, but that subsystem is still readily available and accessible via document attachment. So in 2018, for example, we saw 2 0 days that targeted Flash, but they were delivered via email inside of an actual document. That's what we have this example here, this encapsulation or Matryoshka-capable lures. I can layer them one layer inside of another. It requires some user interaction to actually get to it, but that ends up bypassing security defenses. It's very hard to detect via sandbox and detonation. And there's a myriad of these kinds of samples, right? Some of them are actual vulnerabilities. They have CVEs, like the ones on the screen over here. Sometimes you've got your freebies. Microsoft had this dynamic data exchange vulnerability that at first they denied it was a vulnerability, then they ended up eventually fixing it. It was essentially just a command execution. Like I would send you a document and you open it and it's launching arbitrary commands. I call that a freebie because it was ridiculously easy to exploit. I could teach an audience how to do it in like 3 slides. And then of course you've got what we call uninformed consent. Folks who will enable a macro, for example, and just essentially launch a piece of malware through lack of knowledge. There's a plethora of examples. In the screenshot, we're showing one where it's a real-world campaign. They actually have an embedded binary inside the metadata, and the macro pivots to it. You can see it from this base64 encoded TV. If you look at base64 encoded content, this will kind of stand out to you. But a very common example. So now, next question is, well, where do we dig? Where do we get these things from? There's open platforms like Hybrid Analysis and AnyRun. A lot of guys are doing harvesting on these platforms. They'll go and they'll look at the daily uploads and they'll pull samples from there and dig around that. So that's an option for researchers. You can crawl IOCs that you're pulling off of either blogs that people are publishing, or maybe you have keyword searches on Twitter. And you're now getting IOCs. You can feed to a crawler that goes out and it starts grabbing things and pulling into your corpus. You can map attacker infrastructure, right? So perhaps I've gotten some key finger into attacker infrastructure, and I can map out other domains and IPs and start harvesting lures that way. If you're working at a large company, you can look at your own email spool. There's bound to be a plethora of attacks that are coming in any large-scale enterprise. And then finally, we can focus on VirusTotal. There's a service, if you're not familiar with it, from Google. It's essentially a AV consensus. You upload a file. They'll run it across 60 different engines. They give you the results from there. And for researchers, you can purchase an account and actually get data fed to you from there. I don't think there's anybody that works in the AV industry that does not have access to VirusTotal's intelligence feed. It's very heavily used by folks for fueling their machine learning algorithms. That of course has its own biases associated with it, but it's a very solid and useful platform. I'm terrible at doing this thing lightly. Let me switch to keyboard. So on the attacker infrastructure side, if you're looking to self-source IOCs from wherever it is, Twitter, blogs, whatnot, we've got some public open source tools for you to use where you can pull those things down. The general idea here, though, is you're looking for anchors. A domain name has to be registered by an email address. Of course, that can be anonymized, but if someone is registering multiple domains with the same email, that becomes an anchor where if I find one domain, I can now go enumerate the other ones. Domains resolved to an IP. I can reverse DNS that to see what other domains are on that IP. Perhaps it's a shared server or a Cloudflare server, or maybe there's multiple domains on that IP that are malicious, and each one of these starts pivoting out to other ones. Attackers will typically either stand up infrastructure, so get a server somewhere, make an Amazon, put something on a paste bin, or they'll take over. They'll find WordPress vulnerabilities, scan the web for them, and then just upload their files to it to ensure that these places where they're putting their next stage pivots on, they don't get marked by reputation because they're existing valid sites that have been around for some time. Other things that you can pivot on is some less looked at things like SSL certificates. Maybe someone's using the same SSL certificate ID on 2 different sites, and now you can tie them in that way. Or they're actually tracking their malware campaigns by using Google Analytics, and they have the same Google Analytics ID embedded in there. There's services like Census, for example, that allow you to just search at scale, kind of like a Google of HTML source code, and you can use that for pivoting and finding all these sources to pull it in. So a variety of different things you can do here. And once you do have some anchor, there's a variety of open source tools you can use for pivoting. There's Shodan, there's Gray Noise, domain tools, and a lot of VirusTotal's services are also free. Don't worry about all these slides will be made available and we'll publish them on our blog and whatnot. But here are just some examples for how to pivot on an IP address or on a DNS just using open free APIs. We're going to dive into worm charming over top of VTI, virus total intelligence. So when we're talking about this, we need to look at the scale, right? What are we looking at in terms of numbers? So this was just recently screenshotted, on August 4th. This is typical, you can kind of see it over time. You've got something like 1.2, 1.3 million samples are uploaded to virus total a day. Of those, 1 million of them are distinct. 400,000 there have already been uploaded that same day. Of those, 400,000 are actually, or 900,000 are new and distinct, so they've never been seen before, not just distinct that day. And then of those, about 400,000 are malicious. So we've got 1.3 million samples to harvest from with that little marker in the bottom corner there. Now, if we look at the file distribution, of those files, 400,000 break down to PDF, then 40,000 for Office, 15,000 for Java, 12,000 for Excel, so on and so forth. These are the kinds of malware lures that we're looking at. Add these all up, and you've got about 470,000 samples, per day that you'd have to consider. So now we want to cut through these. To do that, and these are all open source as well. These are YARA rules that are designed for hunting on every sample that's uploaded to VirusTotal. One of these rules will run, and if it fires, that sample comes down to us. So we want to start siphoning off from that, nearly 500K sample set. This one's looking for any document that contains some macro, whether it's benign or malicious. I want that file in our corpus, and that's about 1,000 a day on average. This next one is finding Office documents that contain some kind of ActiveX embedding, or they have some kind of a malicious behavior. Someone thought it had something wrong with it. At least one AV vendor, that's that positive is greater than 0. This produces about 500 a day. Added up to the previous one, that's 1.5K samples a day. This next rule is looking for Java files that are of interest. That's another 500 up to 2,000. RTFs, 2250. PDFs that have some kind of JavaScript, some active content in them. Now we're up to about 2,500 samples, including with Flash as well. So if there's Flash embedded in a document, let's get that thing down as well. So we've already reduced the corpus drastically, right? We've gone from 1.3 million samples to 2,500 a day. Still a bit much for manual analysis, but this is less than 1% of that total corpus. This is a manageable problem for us to be dealing with. So now that you've got these samples, what are some good vibrations that we can use to use this whole worm charming analogy? And this video, by the way, apparently birds do this too. What he's doing here, I'm assuming it's a he, they pat the ground to replicate the feeling of rain, and that brings worms to the surface too. So it's this whole vibrating thing. So some things that you would be not wise to do as a malware author, but great for us on the defender side, is we can look for things that are not malicious, but they're indicative of something that has been generated by a malicious author, or someone that has actually hand created a file format, right? It's not coming out of a PDF, it's not coming out of Word. They've done some modifications to it to evade detections or to make it hard to analyze, but the sheer fact that they've done that has now exposed the content to us. If I'm ever going to try and launch a successful malware campaign, I would want to hide in plain sight. I would not want to use any kind of weird obfuscation that's going to make my payload stand out, especially if I'm bundling zero-day with it. Why am I going to burn an O-day just using an obfuscation tactic that's going to make this sample stand out? Thankfully, people do that, and we can leverage that against them to find interesting signal in the noise. One example is MIME evasions. So, for example, an RTF file starts off with this curly brace backwhack RTF1, but that's not requisite. As long as you have a curly brace backwhack RT, Microsoft Windows is perfectly happy about opening that file and rendering it. So if someone's writing signatures that are looking for RTF files using the full header, they're going to completely miss these files because they're not going to see it as an actual valid RTF file. If you do MIME-based detection, that's not going to show up as a MIME type of rich text format, but it will open by the Microsoft parser. In general, the Microsoft parser is notoriously robust. If you look at this project, it's called the Tiny PE project. One of the hackers posed the challenge of how small can we make a portable executable file and it still executes. And people played with this thing, and they've got these self-referencing header pointers, and they've gotten it to be really, really tiny. It became a little game. So Microsoft is super robust with their parsing, which leaves a lot of room for obfuscation games. Another example of this is the PDF header. This %PDF typically is at offset 0, but actually it could be anywhere in the first 1,000 bytes. And if you open that up in Windows, it will be mapped to Adobe and it will parse it and open it just fine. Other ways that you might burn your 0-day, or how we might catch people's 0-day, is by looking at symbols. If there's JavaScript embedded in a PDF, and there's symbolic information like shellcode and heap spray and ROP gadget, that's great for us. If they're going to leave symbols in their JavaScript, I'm very, very happy to pull that out and use that as an anchor to see what is, what that sample is all about. Another example is this UTF-8 byte order mark. This dates back to 2013, but is still valid today. If you prefix any file with those, the 3 bytes, it will still open and be valid. For example, a zip file, I can put that in front of it. That might break in a bunch of MIME types and be difficult to analyze. But again, not the best thing to do from an attacker's perspective, because you might be burning your wares. And finally, there's chaff. Chaff in essence is just waste. It's things that are superfluous. So like the husk of corn is chaff. And here's an example of chaff around a DDE exploit. So we can kind of see, I've highlighted it here. You can see that DDE auto. And it's broken down. It's broken up among all this like garbage XML that's in between it. I wrote that little regex there at the top, which just highlights all the chaff. Right, so you can see that there is a DDE auto and it's running command.exe and it's pivoting from there to whatever the next stage payload is. So this person has done this to try and mask their payload. But if we're looking for chaff generically, we're going to be able to find any arbitrary payload that's trying to be hidden. Forget about the actual DD auto behind it, just identifying the chaff. Another example, and this came out in February of 2018, guys from Kaspersky, they were looking at the state machine for parsing rich text format, and they found a way that they could put in a pattern where I call it a byte nibble. Like you put in some superfluous bytes, and then a junk byte, and it would just eat it off. So it was just, again, chaff in the middle of it. We talk a little bit more about this later on, but a few months later, some 0-day in the wild, an actual campaign utilized that published byte nibbling technique to try and mask its own payload. Here's an example of that. On the left-hand side, you've got a RTF document that has this byte nibble chaff in it. In the top, I've thrown in a regular expression so that I can pull all that out, and the right is a normalized document. So what's on the left would be difficult to analyze. On the right is a normal form. But on the left, regardless of what the payload is, if I saw that, I know that this person is trying to do something nefarious. That in itself is going to lead me to want to see what's behind that obfuscation. So these are all kind of like surface level examinations, and they'll get us a certain degree, but we need to dig deeper if we want to find more interesting things. So what can we do on that front? We can do sandbox detonation, put up a whole cluster of cuckoo sandboxes and start feeding all our samples to it on a daily basis, letting them detonate in a virtual environment, and then we can look at it behaviorally. We can do static analysis to do like IOC extraction, right? Maybe I'm pulling out any URLs, email addresses, domain names from samples, and then feeding that to a crawling infrastructure and harvesting more stuff that way. This whole hunt pivot crawling that we were kind of touching on earlier. We can also do static analysis via open source tools, and that's what we're going to dive into a little bit further. This is something that anybody can replicate. It's openly, freely available tools. And also, we take this a step further for you later on. As you'll see, we have exposed a ton of data for research. So just some primitives, some tools that we might want to use. When it comes to analyzing Java applets, we're going to want to decompile these things. So there's JD Core, there's the CFR. CFR is my favorite. That's why it's got the champion symbol next to it. JD Core is the fastest. JAD Retro will normalize the version so that more Java can be decompiled by these tools. And again, don't worry about snapshotting this thing because I'm going to fly through the other ones. They're all going to be available. We have tools for Flash. Again, we're trying to get ActionScript out of Flash. We're trying to decompile bytecode with Flash. We've got PDF. We need to decompress streams. We need to grab other things out of it. We need to pull JavaScript out of PDF. Didier Stevens has some great tools for both PDF and OLE. These dissecting these common malware formats. And then of course Microsoft Office. Again, pulling out semantic context with something like these cat doc. or XLSX to CSV, this is pulling out the actual semantic layer. So what was said in the pages of the document, what's in the cells of the spreadsheet. Or something like OLE dump, get the streams out of that thing, take the macro out, decompress it, pulling these things out of that top level format so we can dive into them further. So what we've done is we've taken those YAR rules that we went through earlier, and we connected it to a whole bunch of open source tools. And so on a single daily basis, every time a new sample is fired on with one of our YAR rules, it comes in and we dissect these things at scale. Whether we're pulling it in from crawlers, from VirusTotal, everything comes into this ecosystem. And a key aspect to it is on the right-hand side, you'll see this concept of a VT file scanner and file reporter. So it takes time for the AV vendors to essentially reach a consensus. If I see something today, first time upload, maybe it has 1 AV detection. In 2 weeks, might be 10. In 6 weeks, everybody now suddenly has detection for this thing because there's an echo chamber. Same thing with false positives. All right, so I look at the age, the dust, and the maturity when it comes to a file that has been uploaded to VirusTotal. How long ago was the first upload? When was the last time? What's the time in between? How many times was it scanned? The more of that you have, the more mature the result is, the better of a label that might be. So if you're looking to build if you're looking to use AV labels as machine learning to classify your data set into benign and malicious, doing this kind of rescanning over time is going to be critical because you don't want to fall victim to the industry's own false positive and false negative biases. So let's talk about some real world samples, right? Everything we've talked about is somewhat theoretical. These are all examples of real world zero-day campaigns that were discovered in the wild. Everyone responded to them reactively. So you've got the CVs up there, these are all in the same exact areas that we're talking about. So this .NET and these IEVB scripts, these are actually also reachable from file formats. You don't have to hit it via the browser or whatnot. So these are the same exact malware lures will carry exploits for these CVEs. So let's take a look at these, how we might have found these worms in hindsight. All right, if you look at the first one, CV 2018-8174, this sample was initially uploaded to VirusTotal on April 18th, 2018, and it came from a US-based source. The actual campaign when it launched wasn't until 425. So despite the fact that malware authors know that when they upload to VirusTotal, it's going to an entire community of researchers, still they're using the tool to test their payloads prior to actually launching these campaigns. That's a pretty decent chunk of time. If we can figure out if this sample can stand out to us before the campaign starts, we would have been able to find a zero-day. We would have been able to burn their zero-day before they had a chance to actually launch it in the public domain. So the campaign launched on 425. The next upload to VirusTotal doesn't appear until 5.9. So it had a while to spread before someone somewhere caught wind of it and started pushing it up to the service to see what it was. It came from India, Italy, Philippines, Saudi Arabia, more from the US. On 5.10, you can tell that these are all indicative. When you see, it's not guaranteed that this is how the spread is going, but generally, statistically speaking, as you see it where it's being uploaded from, that's kind of where it's being targeted to as well. So it's kind of spreading out. So on 5.10, we see more coverage. Now, the initial AV detection on this sample was actually quite good. 16 out of 60 vendors were able to detect this thing. It had zero-day in it, but it had a bunch of other things about it that heuristically looked unkosher, and so it stood out. From our perspective, from the things that we've caught, worm charming wise, this thing has got an object update inside the RTF, so that stands out. And this is the one where they're using the RTF byte nibble. Recall that just 2 months prior is when Kaspersky researchers published this obfuscation technique. So just by looking for that, you would have been able to find this zero-day that came across the wire 2 months later. Some screenshots kind of showing detection evolution over time. This is coming from VirusTotal. As I mentioned, great detection up front, but then as it starts sharing, you'll see it starts approaching more of a consensus. And these are just the results. I think this is from the first day scan. Yep, the guys who caught it. Interestingly, there's a lot of overlap, like suspiciously exact overlap in what seemingly is a, not a common name. And you might ask yourself why this is the case. Behind the scenes, it's because a lot of guys OEM each other's products. So when you're looking at AV consensus, you can't just look at it as each vendor standalone. probably all of these guys are OEMing the same exact solution. So when we look at results, we actually weigh all the different vendors. Frankly, half of them are weighed down to a zero because we just don't care about what they think. The other half have some variable weights associated with them, so we can, instead of looking at the positive count, we're looking at the weight count to see when something is interesting. The next example, uploaded on January 22nd, came from South Korea, and only 2 AV engines detected this one off the bat, right? And they heuristically were able to identify the sample as malicious, but it came with an actual flash 0-day. Later, whatever that is, 9 days later, someone discovers this thing and they tweet about it. So here's another way you could have caught it, right? If you're harvesting IOCs from Twitter, again, it was an early warning on 2.1 when this guy's talking about, he puts the word 0-day in there. If you put a 0-day search on Twitter and you look for IOCs and just suck them in, you're going to start getting what people are talking about. So he talks about it on 2.1. Now suddenly, the AV detection jumps up to 9 vendors because there's some public discussion about it, and it shows up on their radars. You start seeing some more uploads on 2.2. By 2.5, 20 vendors have proper detection. And now, how could we have caught this guy? Using the tool set that we just talked about, this is an RTF that has an SWF, a Flash file embedded in it. Again, Flash is dead in the browser, but that's an alive and well subsystem. It's got a great install base, still a good attack target for attackers. Big attack surface. You can do action scripts. You can manipulate memory. If you want to bypass all the built-in compiler and OS protections, you need the ability to manipulate memory some to improve your ability to actually exploit. So it's a good, rich target base from the attacker perspective. So anytime we see a Flash object embedded anywhere, that's super interesting to us, especially if it has very low AV detection. It's not every day that someone's legitimately putting a Flash applet in a document and sending it to someone, while it may happen. In particular, if you run this Flash applet through one of those decompiling tools and pull the action script out, it also tries to do debugger detection. Now, again, this is not 100% guarantee that the thing is malicious. There's digital rights management reasons or just anti-reversing reasons where you might want to do debugger detection, but that stands out. Just those 2 things alone, the fact that it's embedded in a document and it's doing debugger detection is enough for me to really want to dive into it and snag it. Here's the tweet that came out talking about the lack of patch. Attribution-wise, it's always a crapshoot, but the thought process was that this was North Korea sourced attacking South Korea with this O-Day. And actually, it was quite clever. One thing I really liked about it is they had, most malware is multi-stage. It pivots from one stage to another stage. And in this particular case, they looked at some attributes of the system that was being infected before they sent their 0-day down. So actually getting a hold of the 0-day portion of it was a little bit more difficult because you had to essentially replicate the environment that they were looking for in order for that second stage pivot to come down. So on the one hand, they were smart operational security-wise to not burn their O-Day by holding it back, but on the other hand, they burned it by embedding it in a way that was it stands out. AV detection rate over time, again, starting off with a 2 and then settling once it became public knowledge. This is what the actual, on the top right pink, you've got essentially the extracted source code for checking for debugger detection. And then here's just an open source YAR rule that you can use for finding these things. It'll run on the outputs of that action script. The last one is the most interesting one. It was uploaded originally on August 24th, and it had no AV detection at all. Nobody thought it was bad. On 8/24 and 9/12, more people uploaded it. Some folks got hit with this thing and they're like, this looks weird. Let me push it up to VirusTotal and see what the AV industry as on a whole thinks about it. And again, this is 11 additional scans on this file, no detections. Then on 9/12, the 0-day campaign is discovered by FireEye. By the end of the day of 9/12, you've got 2 vendors that have detection. By the next day, 30 vendors have detection for this thing. So you can see it's a very reactive process. So now the question is, how could we have found this one? And again, evasive magic. So they didn't have the full RTF header at the top. They used chaff. In this case, the chaff that they used was new lines all over the place. So it's a RTF file with a truncated header, embeds an OLE object, and they've broken up the text with all the superfluous new lines. So the 0-day, again, stands out because the file format that it's encapsulated in is just odd. It would never have been generated by a real program. screenshots showing the lack of detections, and even over time. From 824 to 912, you've got 11 unique uploads, and every single time, despite the fact there's sharing going on at this stage, nobody is detecting this thing quite yet. So, even after we've captured things, and we're looking at essentially every step of the way, we're pushing things to the side, right? We start off with 1.3 million samples. We brought it down to 2,500 a day. We dissect them with all these different tools to expand out the types of data that's in there. We've got another series of rules that run on top of that to start isolating the ones that might be interesting. But there's other things we can do to cluster these samples together that allows us to then filter them, right? If I've got this huge corpus of malware, if I find one that I don't think is interesting and I can find other ones that are around that are similar, then I can just push those off my radar and not worry about it. So, how can we do this kind of clustering, this kind of filtering? One way is with machine learning algorithms. You don't need to use ML classifiers just to determine what is bad and what is good. I can even further scrutinize and say, this is this kind of bad. This macro was generated specifically by the emotet polymorphism engine. And so if I'm not interested in that because it's prolific and I want to find the needle in the haystack, I write a classifier to identify emotet and I say, okay, push those off, right? There's file specific anchors. If we're exposing this content, this symbolic information, perhaps there's a constant or a variable name that is either generated so it's unique, or maybe there's a constant that's leveraged in some way, some large number, for example, that again can be used as an anchor. So now that I've got all this data, I can say, okay, take this number and then see what other samples have that. Again, push it off to the side. A third option is anchors that are specific to virus total intelligence. When you upload a file to VTI, there's an anonymous uploader ID that goes with it. And so if you're consuming the fire hose, you can keep track of these IDs and you can say, okay, well, what else did that guy upload? I don't know who it is, but I do know that he uploaded or he or she uploaded these, 10 million samples. And so if I find one that might be interesting, I might want to go see all the other ones that person uploaded so I can go harvest through that, that subcorpus. Some notes on clustering. There's a couple of different ways and this could be a talk all on its own. If this kind of thing interests you, we do have a blog coming out in the not so distant future that will describe how we utilize, actually specific to that example, identifying emotet through the usage of our machine learning algorithms. There's some basic things though. This bag of words or a term frequency, inverse document frequency, which is essentially saying, for each word that I'm finding or each variable, and it doesn't have to be just in the semantic layer, it could be in the code layer, how unique is it to this sample? If it's very unique, then again, find all the other ones that are like that, clump them together, push them away. You can do k-means clustering. Instead of looking at semantic features here, where we're picking words, k-means is more about vectorized features. And so the way I look at this is, we have 50% of our features are semantic, 50% of them are what I call visual or structural. Have you ever looked at a piece of source code and you just look at it for a second, it's malicious. It just has that look. It's got gibberish variables. The structure of it looks weird. You can describe that in features. You can capture it by looking at things like average comment length, average variable length, how many variables are there, how many functions are there, what's the psychosomatic complexity. Each one of these things is a numeric feature. We've made a whole bunch of them. It comes out to be about 100. And so you can look at every single document, the embedded logic that's come out of it. You look at the way that it looks by this feature set. Again, you can compare and cluster them together that way. A more generic approach is local sensitivity hashing, or min hashing as it's called. And again, this becomes a very generic method for either taking a vectorized feature set and very quickly being able to compare them, contrast them, and cluster them. We've got a blog on that if you want to read about it. I do want to focus more, however, on, you can use AV detection names if there's something specific to that sample. I can find other samples that were detected with that same name. But I want to focus on one that we find a lot of value in called XMP IDs. This is an IOC that we've been using for a long time. And in talking to folks about it, it's fairly exciting. So I want to talk about that and show how it's done. In general, when we're talking about last note on the ML business is you have to have your data first, your feature selection next, and your algorithm last. As far as I'm concerned, I believe that the entirety of the problem set really lives in the feature selection. You can tune and even fuzz your algorithms. You can throw enough compute power at it to try every algorithm with every tuning mechanism if you wanted to. But really, it comes down to which features you're selecting. So that's why we're talking about this visual, trying to capture what an analyst sees when they're looking at a sample, and then semantic, trying to capture what the intent is. Algorithm-wise, listed from least valuable as far as we found it for this specific problem set to most valuable. Great. They're all good in their own ways, and to some degree, maybe you want to consider weighting above them. Like so, for Excel files, I'm going to put 100% weight in gradient boost. But maybe for Microsoft Office documents, it's going to be 50-50 between support vector machine and random forest. Gradient boost standalone has been the best bang for the buck for us, just in terms of speed and efficacy. But let's talk about XMP IDs. So this is an Adobe format. It's Adobe Extensible Metadata Platform. It was defined, back in like 2012, and in essence, it is a standard for mapping assets, parent to child, and revisions of that child. And it's implemented via original document ID, OID, the document ID, the DID, and then the instance ID, the IID. So if I have and I'll show this in a second actually, so we'll save it off of there. But the key thing here, though, is that it's an XML format, and it's actually updated every time the user updates the asset, and it's embedded within the asset, which is great for us, because that means it's coming with the malware lore. So if we can grab a unique XMP ID, we can use that to pivot to other samples with that same ID. To give you a visual example of how this works, we've got three different documents here, where a document is a graphical asset, like PNG, JPEG, whatever. And you can see the first one's got an OID of dead beef. Every time it's saved, the instance ID changes, and the document ID in this case is the same as the original ID because it's the original. Then we make a copy of it, so we've got the same OID, new document ID. Again, every single saved instance is generating a new instance ID. So in terms of like granularity and amount of fluctuation, your instance ID is going to be moving the most. And then we have a third copy of it, and so on and so forth. There's two formats that we've seen for the actual value of this XMP ID. It's either an MD5 hash, so 32 bytes, or it's a GUID format, so 36 bytes. So, why is this useful? Why do we care about this? We care because graphical assets are very commonly used among malware lures. For example, instead of writing inside the document, trying to convince the user to enable active content by clicking on the yellow ribbon, since folks are looking for that text now attackers will take an image, it's got a Microsoft logo on it, and it says, please click enable content. So unless you're doing something like optical character recognition, you're not going to be able to pull that text out. They've even gotten smarter in recent history, and they're making it even difficult for OCR engines to detect by putting like a blue on blue background text, or making it like a little bit fuzzy. So it'll break the optical character recognition engine. The weakest link in this chain is going to be your user. You send them an email that's password protected and everything looks weird, one of them will undo that thing and launch that payload. The other reason why why this is useful is because graphical assets are commonly lifted from legitimate sources and used in malware campaigns. So perhaps if I'm writing a phish for some bank, I might go to the bank's actual website, pull their legitimate logo, and embed that into my document. Maybe I resize it a little bit, maybe I make it black and white, maybe I merge my layers down, but I took that original asset and I used it somewhere in my malware lore. So if we do hashes of files, that's not great because this tiniest change, of course, the hash is completely different. We can do optical character recognition, that's good, but there's ways of defeating it and it's slow. You can do perception hashing, that's better, but there's again ways of defeating it and it's even slower. But XMP IDs give us the best of both worlds. They carry with the document, they're resilient to change, and it's very, very quick to both extract and look at it. So today, as an example, we watch about 1,000 different XMP IDs, and this is providing a wealth of valuable information for us where we'll see a sample that comes up either in our customer network or it comes from VirusTotal, has no detections, but we know it's bad because we're tracking these XMP IDs that are being reused from campaign to campaign. Another example on this front is, I don't know why this woman got chosen, but she's a researcher in EU. They had made a resume for her. They used her profile to send malware lures out. And so once we pulled out that XMP ID, we looked at our corpus, and there was hundreds of different unique malware samples that were used in this poor woman's face in order to go infiltrate whoever they were sending that resume to. So, we've covered a lot of things, and it'd be nice to be able to play with it. I'm a big proponent of hands-on. And so towards that effect, we're announcing this labs.inquest.net. And so it's live now, and it gives you access to, instead of having to build all those things yourself, from the YARA rules, the malware sample harvesting, to the extraction and the indexing, it just gives you an open API, both interactive through the web interface and just open API access to it. You can pull all sorts of data, do all sorts of searches. There's 4 really main components to it. One of them is a document dissector. So you can upload files to it if you want and get them dissected. You can upload hundreds of files to it if you'd like. We've seeded it with about 1 million samples. Half of them are exposed right now. We'll expose the other half at a future date. So that's one key component of it. Give it some malware lore that's a Matryoshka doll of encapsulation, and it'll dissect it and extract the semantic layer. It'll do optical character recognition. It'll pull out IOCs. It'll pull out the embedded logic. It'll do some decoding. It'll make your life as an analyst, just much easier for both upload and querying it. We've also open sourced a bunch of YARA generators and helpers. We use YARA daily in a number of different ways. And so to help make our lives easier, there's some things that are very manually tedious to do. And so we went through the extra manually tedious process of automating it one time. And that allows you to just do it. So things like if I'm trying to write a rule that is for hex encoded content, but I want it to be mixed case, that's a pain in the ass to write. I can do it once, and this will generate it for me now. I can convert strings to uint conditions as a performance boosting thing. I'll let you guys go read about it on the actual site. The most impressive one, I think, is the base64 regex generator. We're able to take regular expressions that you write for plain text, and we will spit out the base64 encoded version of that regular expression. As a real world example of how we use this today with great results, we've taken a whole bunch of PowerShell directives that we consider to be malicious, and we've generated a bunch of regexes for it, fed it through the system, and now we've got a YARA signature that's looking for fileless malware that has weird PowerShell pivots in it. You can even do it twice. So if you want to do double base64 encoded, you can. If you want to do wide char base64 encoded, you can do that as well. So all that is available. As an example, if you hit this, it would just work. Here's API-driven example where I'm giving it PowerShell and it's giving me back hex encoded variable case. Here's one where it's converting the RTF magic at 0. Instead of having a string comparison, which is slow in high throughput terms, this is converting it to an integer dereference, so it's instantaneous. Is this value at that address, as opposed to scan the entire document for these values and then show me where it's at. And then the base64 regex generator. And you can see, if you can believe this, at Tipping Point, we used to write these things. And it was a nightmare to write and a nightmare to compare. So we ended up at some point building a tool that automated this process for us. So you can send a string up to our cloud service and we'll just send you back the regular expression. I will say that this can get messy real fast. If you go too far with it, there's no regex engine in the world that's going to run that thing at any kind of reasonable speed. So, caveat emptor on that front. I mentioned everything else is API accessible. There's 2 other tools that we've exposed through it. One of them is a reputation aggregation. So we have aggregated like 24 different sources into a single searchable interface. So again, you can use that as a source of places to go pivot off of to pull down more malware samples and whatnot from. And finally, IOC aggregation from Twitter. There's a lot of people that we follow that we think do neat work. Generally, when they put out some kind of URL or hash, like we'll go check it out. And so this is just an aggregation of all of that as well. And again, entirely API accessible. And with that, if you guys have any questions about the work, or you want to work together on any interesting samples, please don't hesitate to reach out and get in touch. And just a quick thank you to some of my colleagues for sitting in the audience and helping me out with all this. William MacArthur, Amir Niakan, who some of you guys may know as Dissect Malware. He's pretty prolific on Twitter, and Adam Luciano. Big thanks to them for helping me put all this together. But thank you guys very much. I appreciate it. And just open up to any questions you might have. If you do have questions, there's mics in the middle aisles. Otherwise, I'll be hanging around for a little while. On another note, if you enjoy my couture over here, we do have a bunch of t-shirts in the back. Adam would be happy to hook you up with one. Any questions? Yeah, they're going to post the slides, and if you just later on today, when I get back to the hotel, just do blog.inquest.net, and we'll have it up there. All right.
Hello. So I think should be an easy question for you. How have you been able to tie back when you do find an exploit within malware to the correct CVE? Are you doing a lot of bin diff analysis when patches are being released, and that's kind of helping you at that level of attribution, for lack of a better term?
So the question was, how are you mapping, when you see an exploit, how do you then map that to the CVE? If it's already been published, chances are one of your tools are going to label it on their own. When you're looking for, like if we were to write a signature, for example, to detect a specific CVE, I'm writing it specific to it. So when I see it fire, I see that that is what it was. If you find something that is exploiting your system and you're fully patched, it's an ODay, you're then going to have a CV associated with it, moving forward. So it's, whether you're looking at it in hindsight or looking at it forward, that's the answer there, if that makes sense.
Would you say for you in practice, it's better to run a fully patched system that you're executing your malware on, or do you run vulnerable systems?
If we're looking for this kind of thing, where we're looking for an ODay, you want a fully patched system. You want it to be a system where if something did get compromised, it's interesting. Otherwise, if you're shooting for like Windows XP or some of the low-hanging fruit, there's going to be plenty of noise there. So I would go with a fully patched system that you expect to see in production.
Thank you for being generous with your knowledge. Thank you.
Okay, thanks.